The physical dependence of the drop in activity compared with the concentration is a mutual attraction of particles. Mutual repulsion of particles in solution should cause an increase in activity. In dilute electrolyte solutions, the electrostatic attraction of ions is predominant and it decreases with increasing concentration. Taking into account the intrinsic size of ions is equivalent to taking into account the repulsive forces that do not allow the ions to come closer to a distance less than a. The second approximation of the theory, taking this factor into account, leads to a less sharp decrease in the activity coefficient, and it allows to describe the experimental data in a wider concentrations range. However, in concentrated solutions, most of the water molecules are bound by ions, so the addition of new portions of electrolyte should be accompanied by the destruction of solvate shells and the overcoming of the forces of the ion-dipole interaction. This is equivalent to the predominance of the effect of mutual repulsion of ions over their mutual attraction. Thus, the transition to concentrated solutions is accompanied by a sharp increase in activity coefficients. To describe the increase in activity coefficients at high solution concentrations, an empirical term was introduced into the equation of the second approximation of the Debye-Hückel theory. And the formula has acquired the appropriate form. The resulting equation is known as the third approximation of the Debye-Hückel theory. An empirical selections of the constants A and C can describe the experimental data on the activity coefficients for concentrated solutions. The equation of the third approximation of the Debye-Hückel theory has a simple form, but the constant does not have a definite physical meaning.